Okay, so we are done with rotations, and typically at this point we have two options. One is that we do a bit of astronomy, very baby astronomy, as in you look at the orbits of planets and see how those are described by Newton's laws, and that's where everything comes together. You have Newton's second law, you have to look at Newton's second law, you have to look at rotations and so on and so forth, okay? The second route is that you look at simple harmonic motion. Again, you can have lots of examples over there which involve basically everything that we have learned in this course until now. So these are two basically capstone lectures, this lecture and the next lecture. We'll focus on simple harmonic motion, because I personally feel that yes, it's nice to look at stars and planets and so on, but of greater practical relevance is simple harmonic motion, okay? So I'll focus on that, but now, I should emphasize that you have all the tools that you need in order to understand how the planets exactly go around the sun. How does Newton's second law, how does Newton's law of gravitation predict these elliptical orbits, okay? Okay, so simple harmonic motion. Of course, अगर आपको simple harmonic motion याद आए, if you hear the phrase simple harmonic motion, the first thing that you visualize is probably a simple pendulum. The simple pendulum is actually not the simplest example of simple harmonic motion. It's not that straightforward as you have been led to believe. Another popular example, of course, is of a block attached to a spring. You can do this vertically, you can do this horizontally. Doing it horizontally is simpler because you don't need to worry about gravity, because the effect of gravity will be balanced out by the normal force. And basically, if you pull this block just executes this to and fro motion, which is your characteristic feature of simple harmonic motion, okay? So now the first question that you of course have to ask, that this looks like a very special case. Why are we so much hell-bent on studying this simple harmonic motion when it really only applies to blocks and springs and some very particular cases? It's actually, the first thing that you need to understand is the following, okay? Any system in stable equilibrium any system in stable equilibrium, okay, and systems and objects generally go to a configuration of stable equilibrium. So for example, if you have this bowl and you release a small sphere from here, this sphere will go like that, 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 eventually we settle down at the very bottom of the bowl, essentially, and it will remain there. Because essentially at that point the net force acting on this object is zero, the net torque acting on this object is zero. Once the object reaches equilibrium, it stays there. वो कर देखते हैं, okay, उसकी तरफ, okay. So objects and systems generally tend to evolve towards stable equilibrium. And then once they are in stable equilibrium, if you nudge such a system slightly, and again I'll quantify what do I mean by slightly, that system will execute simple harmonic motion. That's why you see simple harmonic motion all over the place. If you have any system whatsoever, it's in stable equilibrium, you disturb it slightly, you get simple harmonic motion. It basically is the same motion as your block spring system, even though there may not be an actual spring involved. Okay? Okay? So let's look at that in more detail. Just to be more concrete, I'll take the example of two atoms. दो atoms हैं, उधर आपको कोई भी spring नहीं नजर आ रहा. Okay? And I'll show you that two atoms, when you bring them close together, of course, generally they form a molecule. And if you then disturb one of these atoms slightly, that atom will start to execute simple harmonic motion. So it's basically as if there's a spring that is joining the two atoms. Okay? Acha. The characteristic feature of this block spring system is that if you place the origin over here, you pull this slightly, there is a restoring force acting on this block. So over here, if that is the direction of my x-axis, if I pull this slightly to the right, then x is positive for the block, and the force that is acting on the block is to the left. With the choice of my coordinate system, when x is positive, the force acting on this block is negative. And we know from Hooke's law that the magnitude of the force is proportional to x, and the constant of proportionality, of course, being the spring constant. If the block is on the other side, if the block is to the left of the equilibrium point, then the force that the spring exerts on the block is to the right. Okay, so that's why we write down that the force that the spring exerts on the block is minus kx ex. This minus indicates that this is a restoring force. This force always tries to bring the block back to equilibrium. If the block is to the right of the equilibrium point, the force is to the left. The force is trying to bring it back to the equilibrium point. If the block is to the left of the equilibrium point, the force is now to the right. That's what this minus sign ensures. If x is positive, the component is negative. If x is negative, the component is positive. Okay? Right? That's the characteristic feature of simple harmonic motion. You have this linear restoring force. It's called linear because the force is directly proportional to the disturbance. The disturbance in this case being x. X, remember, is just the distance of the block from the equilibrium position. Okay, so you have a linear restoring force. So keep that in mind. Okay. Now let's move to another system. उस पे वापस आएंगे. But let me just move to another system. You have two atoms, and for simplicity, I arrange them along on one straight line. And you bring this second atom closer and closer to the first atom. And I say, plot the potential energy as a function of the distance between the two atoms. Okay? So you are supposed to plot the potential energy. Now, of course, your first tendency will be, sir, मुझे वो function दे u of x ताकि मैं उसका graph sketch कर सकूं. I don't know. I don't have that function. I don't have an analytical form of that function. I don't have an equation that describes that function. You are supposed to deduce the general features of this function from physical principles. At infinity, of course, u is 0. As you bring the second atom closer and closer to the first atom, so I'll keep the first atom fixed at the origin. Okay, so I'll imagine that the first atom is fixed in place. You're bringing the second atom closer and closer to the first atom. As you bring it closer and closer to this atom exerts an attractive force on this atom. So that means that the slope of this graph should be, if I'm taking that direction to be positive, the slope of this graph should be positive so that the force is negative. Okay, the force pointing like that is a negative force with my choice of coordinate system. And remember, where is this coming from? इसलिए मैं कहता हूँ simple harmonic motion is a nice place to conclude because you basically go through everything that we have done in this course. याद आया? The force is equal to minus du by dx. How do you define the potential energy function? The change in the potential energy between 2 points equals the negative of the integral of the force over between those 2 points. So in particular, if you're looking at the potential energy function at a point, you take a reference point xp and you do that. ये याद आया? That is your definition of your potential energy. This is how you compute the potential energy. You choose a reference point, you calculate the change in the value of this potential energy function between the reference point and the point at which you are calculating the potential energy function, वो point x है. This is the negative of the integral of the force, right? And then because we argued, as you saw, that only differences in this function matter, so this constant doesn't matter, this is just a number. You can just set this number to be equal to 0 for convenience, so just left with that. Okay, for the gravitational force, this reference point, the convenient choice of this reference point is at infinity. For Hooke's law, this convenient choice of this is x is equal to 0, and so on and so forth. Okay. Now from this, if I take the derivative on both sides, ये 2.5 लाख रुपए का सवाल है because this involves 2 courses. 7 credit hours 2.5 लाख से भी ज्यादा बना है. ये किसके बराबर होगा? Negative f of x. From the first fundamental theorem of calculus, you're differentiating this integral with respect to the upper limit. So what you'll get is this thing evaluated at the upper limit, which is that, this minus sign is just that. And therefore the force is the negative of the derivative of the potential energy. So if you know the potential energy, you know the force, and vice versa, of course, because potential energy is the integral of the force over distance, and then correspondingly, of course, you can go the other way around. This is nothing other than your well-known thing that you learned in high school, that differentiation and integration are in some sense inverses of each other. Okay, so then with this relationship, keeping this relationship in mind, I need to sketch this graph. तो सब फर्स्ट ऑफ ऑल अगर पोटेंशियल एनर्जी इंफिनिटी पे अगर 0 है, इधर पोटेंशियल एनर्जी जो है फॉर फाइनाइट वैल्यूज ऑफ एक्स नेगेटिव होगी, पॉजिटिव होगी? नेगेटिव होगी बिकॉज इट्स अ बाउंड स्टेट. You need to give the second atom some energy in order to escape it to infinity. क्योंकि वो पहले एटम ने उसको अट्रैक्ट करके पकड़ा हुआ है. Okay, so its energy must be less than 0 because so that you give it energy and then its energy becomes bigger than 0. Okay, so it must be negative with the positive slope. Why a positive slope? क्योंकि force negative है. When the second atom is experiencing, this atom is experiencing an attractive force, a force to that in that direction. आपने एक्सिस उस डायरेक्शन में ली है. Okay? और फिर ऑफ कोर्स जैसे जैसे एटम करीब आता है इस एटम के, फोर्स इंक्रीज होती है, डिक्रीज होती है जनरली इनिशियली तो इंक्रीज होगी ना, सो दैट्स व्हाई द स्लोप विल गो लाइक दैट. अब जब ये एटम बहुत ज्यादा करीब आ जाता है इस एटम के, व्हाट हैपेंस टू द फोर्स? You get repulsion essentially, because the two electron clouds will overlap and you'll get a big repulsive force. तो इधर जो है केमिस्ट्री इंटरडिसिप्लिनरी नेचर हो गया. तो इधर जो है आपका बड़ा सारा एक लाइन मिलेगी विद अ ह्यूज नेगेटिव स्लोप. Negative slope of course means a big positive force, and positive force in this context means a big repulsive force. तो इन दोनों को ज्वाइन करना है आपने, तो there must be then a minimum point. यह भी आपका थ्योरम गारंटी करता है, कैलकुलस का थ्योरम, कि एक मिनिमम पॉइंट आएगा फिर. So you have this minimum point. इसका मतलब है दो एटम्स को आप इंटरेक्ट करने दो, they will form a molecule, और ये फिजिकली क्या है in chemistry terms, what is this length equal to? The bond length. तो ठीक है, आपका मॉलिक्यूल बन गया. The two atoms on average remain this much distance away from each other. अब किसी वजह से सपोज करो इस एटम को थोड़ा सा झटका लगता है. The atom, instead of being this distance away from this first atom, is now this much distance, is now a further distance away. अब इस एटम को क्या होगा? आपको झटका लगा और फिर झटका खत्म हो गया. जस्ट लाइक आपने ये स्प्रिंग को खींचा है और फिर छोड़ दिया, उसके बाद वो ब्लॉक जो है स्प्रिंग फोर्स की वजह से इवॉल्व कर रहा है. इधर जब आपका सेकंड आइटम है उस पर क्या फोर्स लग रही है, किस किस्म की फोर्स लग रही है? व्हाट्स द डायरेक्शन ऑफ द फोर्स? इज टू द लेफ्ट, क्योंकि इधर स्लोप पॉजिटिव है. तो एटम जो है ये दूसरा एटम वापस आएगा पहले एटम की तरफ. लेकिन वंस इट रीचेस ओवर हियर, इट्स नॉट स्टेशनरी, इट ओवरशूट्स, क्योंकि वो ऑलरेडी मूव कर रहा है, इनर्शिया. ओके, सो इट ओवरशूट्स, इट गोज टू द अदर साइड. लेकिन जब इस साइड पे आई, आप किस डायरेक्शन में फोर्स लग रही है? So then it slows down, it comes to a stop, but then it doesn't remain at a stop because there's a still force acting on it, and then it starts moving backwards again like that. Or फिर it's accelerates. At this point again the force is 0, but it's moving, so it again overshoots, इधर आ जाता है. So you can again see वो atom आपका simple harmonic motion का है. और अगर आप इसको गौर से देखो, you don't need to be a mathematician, you just need to be a bit of eye test है. इसके पार्ट का अगर मैं zoomed up वर्जन बनाऊं, ये सिर्फ ये आपके ग्राफ की, forget about this shape of the graph, forget about this shape of the graph. what is the shape of the graph in this region looking like? A parabola. Yeah, you can prove it in calculus that near a stationary minimum point, or near a stationary point in fact, the any function looks locally like a quadratic function or a parabola. Okay? Either minimum point, so you have an upside, correct way up parabola. If you have the maximum point, you would have an upside down parabola. Okay? Let's prove this. Okay? तो पहला काम हम ये करते हैं कि सर आपको देखा आपके फोर्स ये लीनियर फोर्स आ रही है, तो इस केस में कॉरेस्पॉन्डिंगली स्प्रिंग ब्लॉक सिस्टम में पोटेंशियल एनर्जी का फंक्शन क्या होगा? किस फंक्शन को मैं डिफरेंशिएट करूं तो ये आएगा हाफ के एक्स स्क्वायर, राइट? माइनस साइन तो खुद ब खुद आ जाएगा, बिकॉज टू गेट द फोर्स आई नीड माइनस डी यू बाई डी एक्स. ये क्वाड्रेटिक फंक्शन है. For the spring block system, the potential energy is quadratic with the displacement. And you can immediately see कि अगर वो दूसरा आइटम थोड़ा सा डिस्टर्ब होता है फॉर्म इक्विलिब्रियम, this is basically the same thing as that. इधर भी तो पैराबोला ही बन रहा है, उधर भी पैराबोला बन रहा है. Okay, so about the equilibrium, if you are getting a parabolic, a quadratic function for the potential energy, you are basically back to your block spring system, even though there is no spring over here, of course. दो एटम है. ओके, सो लेट्स लुक एट दैट. इसको मैं कहता हूं x नॉट. आई से एक्सपैंड दिस फंक्शन u ऑफ x अबाउट x इज इक्वल टू x नॉट. क्या करोगे? वन ऑफ द फ्यू थिंग्स दैट यू मे रिमेंबर इज द नेम टेलर. देयर वाज समथिंग दैट वी डिड, टेलर सीरीज. यू कैन राइट डाउन दिस फंक्शन, द होल फंक्शन, बाय यूजिंग द प्रॉपर्टीज ऑफ दिस फंक्शन एट दिस पॉइंट, at the minimum point, जिसको मैंने x is equal to x naught का है. So u of x by the Taylor series is equal to u of x naught plus du by dx calculated at x is equal to x naught multiplied by x minus x naught plus 1 over 2 factorial double derivative of u with respect to x calculated at x is equal to x naught multiplied by x minus x naught whole square plus so on and so forth. Okay, now again for convenience I can set this thing to be equal to 0. Kyun? Because again for any potential energy this is just a number. I can set the potential energy function, you can add any constant to it that doesn't change anything physically. So we might as well just add 0. ये किसके बराबर है number? Yeah, sure, but force at which point? और वो किसके बराबर है? 0. The slope, this is the slope of this function at this point. Okay, this is just equal to 0 because you are expanding about the stationary point. और अगली टर्म क्या है? Well, ये तो कोई number है, right? This is just a number which I can just write as half times k. K कोई spring constant नहीं है इधर, of course. This is just the numerical value of this double derivative. लेकिन what I'm left with is that u of x for this two atom system is effectively half times k times x minus x naught whole square. In other words, क्योंकि u of x naught मैंने किया है, what people do is that for further convenience वो कहते हैं बजाय ये axis choose करने के ये क्यों नहीं axis choose कर लेते, ये एक्सिस चूज कर लेते हैं. इस केस में देखो आपको बिल्कुल ही सिंपल सा पैराबोला मिल रहा है. यू डोंट इवन हैव दिस x माइनस x नॉट बिजनेस, क्योंकि x नॉट अब आपने नए कोऑर्डिनेट सिस्टम में x नॉट 0 कर दिया और आपका पोटेंशियल एनर्जी एट 0 इज 0, जो कि आपने इधर सेट भी किया था. ओके, इधर. Okay, so then you simply arrive at the u of x is equal to half of kx. Even though again the point is there is no spring and yet there is a spring effectively. ये पूरी फिजिक्स मैथमेटिकली वैसे ही है जैसे कोई स्प्रिंग है दरमियान में, even though there is no actual spring. Okay? Again आप कहोगे सर वो अगली टर्म्स भी तो होती हैं टेलर सीरीज में. आई एम assuming that that's where this statement comes in. Disturb slightly. When I disturb it slightly, that means that x minus x naught is small. So x minus x naught whole square is considerably bigger than x minus x naught whole cube. As in, the next term in this Taylor series is considerably smaller than this term in the Taylor series. Then I can just truncate the Taylor series effectively over here, and then I just have that. The physics that this problem, this 2-atom problem will display is exactly the same as the physics displayed by this block spring system, because the potential energy function is effectively exactly the same. The force is effectively exactly the same. जो force ये दूसरा atom experience कर रहा है near the equilibrium point is precisely the same as a spring force. That is proportional to the displacement of the second atom from the equilibrium position. It's pointing in the opposite direction to x, and so on and so forth. Okay. So hopefully this goes along some way towards convincing you that why simple harmonic motion is so important, because all physical systems naturally evolve towards equilibrium, and if you disturb a system in equilibrium slightly, voila, simple harmonic motion. Okay, so but before we go on, let's look at the mathematical consequences of the force being equal to that. ये तो हमें पता चल गया कि force for any system near equilibrium, at equilibrium, if you disturb it slightly, effectively उसमें force इस form की होगी. But what's then the consequence of this force? What does the motion of this system look like? To do that, of course, we can just go to this system, because now we know effectively that any physical system at equilibrium disturbed it slightly, it's effectively the same as this system. So I have to describe mathematically the motion of this block. कैसे करूँगा? क्या चीज़ इस्तेमाल करूँगा to describe mathematically the motion of this block? You look at Newton's second law. You look at Newton's second law and you say that, okay, minus kx, Ex, that's the force acting on the block, must be equal to the mass times the acceleration. You're only looking at the horizontal acceleration, of course, in this case. So I write the horizontal acceleration in this case as that. This is simply the total force equals ma. Vertical the force कोई लग ही नहीं रही, total force on the block. And therefore, from here, I can write that the double derivative of x with respect to time equals minus k over m times x, which for future convenience, I write in this way. Minus. I define this omega naught square, this quantity as k over m. This is just to clean it up, okay? Clean up your constants. K is a constant, m is a constant, k over m is another constant. I have just introduced a new symbol for this k over m constant. Okay. Right. So the solution, the equation that you're looking at, that you have to figure out what does it mean, is the following. Again, I must emphasize that for any system which is in equilibrium, you disturb it slightly, you effectively will then have to solve essentially exactly the same equation. So it's not just a block spring system. I'm just taking that as an example. As we have seen, essentially any system at equilibrium disturbed slightly, that's basically the same as your block spring system, and therefore the mathematical treatment is also the same. Omega naught scale, omega naught, as you'll see, will be related to the natural frequency of this simple harmonic motion. I still, of course, have to say कि ये क्यों है simple harmonic motion, ये oscillatory nature किधर से आ रही है ये block के motion की, and now we are going to, that's what we are going to look at. This is mathematically what is known as a differential equation. Of course, Newton's second law is also a differential equation, because the thing that you need is trapped inside a derivative. The thing that you eventually need from Newton's second law is where is the object at different times. Most of the time, that's what you are looking for. A differential equation is any equation in which the thing that you are solving for is trapped within a derivative. इधर आपने x निकालना है, देखो x जो है डबल डेरिवेटिव के अंदर फंसा बैठा है, इधर भी फंसा बैठा है, but double derivative के अंदर भी फंसा हुआ है. Okay, so any equation in which the thing that you want is trapped inside the derivative is a differential equation. This is known as a second order differential equation simply because it's trapped inside a double derivative. Okay, ये इतनी बातें करते रहते हैं. Okay, so now we have to solve this differential equation in order to extract out कि x क्या होगा. Okay, so how do you solve a differential equation? You can take a couple of courses on solving differential equations. I shouldn't say this on camera, so I won't say it. But you know, by and large, they're not that useful in practice. In practice, the most common technique of solving differential equation is that you guess the solution and see whether it works. Okay, so and you have to guess it piece by piece. Okay, so let's in essentially what I'm asking is find a function x of time t. It needs to be a function of time t because you are differentiating with respect to time t. If it wasn't a function of time t, then of course the double derivative of x with respect to t would just give you 0, but that's not obviously true. Of course, sir, x is equal to 0 is a solution. Of course it's a solution, but that's the most boring solution possible. आपका स्प्रिंग कुछ भी नहीं, आपका ब्लॉक कुछ भी नहीं कर रहा, it's just stationary. Okay, I thank you. I already know that will be one possible solution. Okay, you leave the block as it is, it will remain put. Okay, I'm looking for the more interesting solutions of this equation. Okay, so beyond this trivial solution x is equal to 0, what other solution can we have? You're looking for a function x of t such that when you differentiate it twice, you get back the same function. Multiply with this constant, multiply with this minus sign. Whenever you differentiate a function, you get back the same function, your immediate thought is the exponential function. That you immediately throw away because in this case, first of all, you know that exponential behavior नहीं हो रहा. Exponential behavior just grows and grows and grows or decays and decays and decays. इस case में to and fro motion हो रहा है. So it shouldn't be an exponential function. That comes along with the qualifier. It can be an exponential function with a complex exponent, but since I'm not doing complex numbers in this course, I'll stay away from that. Okay. But anyway, it cannot be a complex function. It cannot be an exponential with real exponents. Okay, because if you have an exponential function with real exponent, something like that, इसको दो दफा डिफरेंशिएट करोगे, आपका ओमेगा नॉट स्क्वायर तो नीचे आ जाएगा, लेकिन माइनस साइन नहीं आएगा नीचे. आप कहोगे सर माइनस साइन के लिए ये कर दें. दो दफा डिफरेंशिएट करोगे, माइनस ओमेगा नॉट दो दफा आएगा, माइनस माइनस प्लस हो जाएगा, दोबारा ये नहीं आना. अगर इधर आई डाल दोगे फिर आ जाएगा. But that's not in this course. So never mind. You have to wait until modern physics. Okay. So I know आप बड़े impatient हो गए. Just wait 5 weeks. Okay. So anyway. क्या चीज? और वो भी नहीं काम करना. चेक कर लो. इसको दो दफा डिफरेंशिएट करोगे, ये माइनस साइन वैसे का वैसे रहेगा. इसको जब करोगे इधर डालोगे तो माइनस माइनस प्लस हो जाएगा. हाँ, उसी की तरफ आ रहा हूँ. Okay, so the exponential function is not going to work. You try instead the trigonometric function. Of course, that is again you could motivate it from the fact that to and fro motion and trigonometric functions display this cyclic behavior. So you first of all try, for example, cosine of t. That is your first guess. Why is this guess wrong? Well, first of all, आपका argument गलत है. The argument of the cosine function should be dimensionless. इधर आपका argument की dimensions time की हैं. So first of all, you go over here and say, okay, omega naught square जो आपने define किया है, सर जी इसकी dimensions क्या है? इसकी dimensions work out करते हैं, okay? K की dimensions क्या हैं भाई? Force divided by distance. Force की क्या dimensions होती हैं? Mass times acceleration, right? और फिर force over distance होता है, तो ये हो गया जी आपका, ये खत्म हो गया. And then you have divided by mass, तो kg कट गया. You have second inverse square. ये omega naught square की dimension है. So omega naught की dimensions क्या है? Inverse time की. So omega naught does have the same units as frequency essentially. Okay. So if I multiply this with omega naught, I immediately get something dimensionless in the argument, which is what I want. And of course, another way to see that is कि दो दफा इसको differentiate करूँगा तो you'll get 2 factors of omega naught outside, which is exactly what you want. Okay, so if you differentiate this twice, what do you get? You get minus omega naught sine omega naught t from the first derivative. From the second derivative, you get minus omega naught square cosine of omega naught t. और ये ही आपका जो ओरिजिनल फंक्शन है, जो आपकी ओरिजिनल गेस है वो इधर मौजूद है. सो यस, दैट इज द सॉल्यूशन, एक्सेप्ट दैट दिस इज आल्सो रॉन्ग ऑन फिजिकल ग्राउंड्स. इसमें अब क्या गड़बड़ रह गई है? अगेन डायमेंशंस गलत हैं. कोसाइन का आउटपुट की क्या डायमेंशंस होती हैं? नो डायमेंशंस. लेकिन आप ये लिख रहे हो कि x ऑफ t इसके बराबर है, तो ऑफ कोर्स यू नीड सम कांस्टेंट विद डायमेंशंस ऑफ x1 की तरफ आते हैं. ओके, विद डायमेंशंस ऑफ पोजीशन व्हिच इज द एम्पलीट्यूड ऑफ दिस मोशन, क्योंकि कोसाइन की वैल्यू -1 और 1 के दरमियान हो सकती है. तो x की वैल्यू अब क्या किसके बराबर हो सकती है? -a और +a के दरमियान. So a is basically the amplitude of this motion. If you sketch this motion, you basically have a graph जिसकी y values जो हैं are restricted between -a and +a. लेकिन इसमें भी गड़बड़ है. इसमें क्या गड़बड़ है? हाँ जी भाई, पूरा कैलकुलस का कोर्स लिया है, पैसे हलाल करो. Your time to shine has come. Okay, एप्सिलॉन डेल्टा की जंजीरें तोड़ मारो, कर लो कैलकुलस कोई. नहीं, लीनियर फंक्शन नहीं काम करना. देखो, डबल डेरिवेटिव आ रहा है. योर एक्स क्या है? एग्जैक्टली, योर एक्स इज ट्रैप्ड इनसाइड द डबल डेरिवेटिव. आई एम टू लेजी टू डू 2 इंटीग्रल्स टू एक्सट्रैक्ट एक्स. लेकिन आई हैव टू डू 2 इंटीग्रल्स फंडामेंटली टू गेट आउट एक्स. 2 integrals will lead to 2 constants of integration. आपका ओमेगा नॉट कांस्टेंट ऑफ इंटीग्रेशन नहीं है. ओमेगा नॉट तो मुझे ऑलरेडी पता है. I don't need to figure out the value of omega naught from some initial condition. Omega naught तो मुझे ऑलरेडी पता है. That's not a constant of integration. I need 2 other constants of integration. एक तो a है ऑफ कोर्स, और कौन सा कांस्टेंट है? और ऑफ कोर्स आपको कहीं और कांस्टेंट डालना है. द ओनली सेंसिबल वे टू डू इट, देयर आर अदर वेज टू डू इट, इज वन सेंसिबल वे टू डू इट इज दिस. क्या आपका ये जो एंगल है इसमें भी तो कोई कांस्टेंट ऐड कर सकते हो ना. एंड नाउ ऑफ कोर्स यू हैव टू से दैट इट डज द गेस स्टिल वर्क. इसको अगर डिफरेंशिएट करो विद रिस्पेक्ट टू टाइम, व्हाट डू यू गेट? यू गेट माइनस ओमेगा नॉट a sin omega naught t plus phi. And then you differentiate this again, what do you get? You get minus omega naught square a cosine omega naught t plus phi. ये क्या चीज है? x of t. So you have that the double derivative of x of t is minus omega naught square times x of t. Okay, so you have that. So this guess does work. Okay, and it contains 2 constants that you have to figure out from the initial conditions, a and phi. Okay, अब आपको ऑफ कोर्स कहोगे दिस इज वेरी सिमिलर टू कि अगर मैं कोई क्वाड्रेटिक इक्वेशन आपको दूं, फॉर एग्जांपल, और मैं कहूं कि कोई आई प्ले अराउंड विद वैल्यूज ऑफ एक्स सच दैट द लेफ्ट हैंड साइड बिकम 0. I found the root of the quadratic equation. I play around some more and find another value of x such that the left hand side becomes 0. I found another root of the quadratic equation. मैंने कोई quadratic formula नहीं लगाया. I've stumbled upon, I've guessed the correct answer. But then कोई उसी वक्त आपसे पूछेगा आपको कैसे पता कि भाई आपकी यही guesses सिर्फ हैं? कोई क्या पता कोई और value of x be that could also be a solution of this quadratic equation. How do you know? Maybe there's a third answer that you haven't discovered. उसको क्या जवाब दोगे? There is a theorem in mathematics called the fundamental theorem of algebra that says कि अगर आपकी quadratic equation, I mean one form of that says कि quadratic equation है that can have at most 2 real roots. अगर कोई cubic equation है that can have at most 3 roots, sorry. अगर आपकी quadratic equation है that can have at most 4 roots and so on and so forth. So you resort to that theorem. कि quadratic equation अगर मैं 2 of my guesses worked, That's it. There is no other solution. There is a similar theorem for differential equations. For simple second order differential equations, if you have a solution that contains two constants, that's it. That is the solution. There is no other solution. Okay, this is something called the uniqueness theorem. Okay, कि आपका solution unique है. Okay, anyway, मैंने इसलिए बताया कि शायद किसी के पेट में दर्द हो रही है कि सर ये तुक्का मारने के वाली मेथड जो है मुझे पसंद नहीं आई. तुक्के वाली मेथड की there is a strong theoretical foundation behind it called the uniqueness theorem, which guarantees कि अगर तुक्का काम कर गया है, that's it. Okay, you don't need to lose sleep over it. Okay, that is the solution. Okay, अच्छा. Okay, so now of course, what we have done until now is, okay, given this equation, the solution is the following. Of course, we already have some idea कि physically A का क्या मतलब है. A is basically the amplitude of your motion. Phi का physical मतलब क्या है? If I send you to the lab और आपको ये ब्लॉक स्प्रिंग सिस्टम जो है ये ब्लॉक ऑसिलेट करता हुआ नजर आता है, एंड मैं कहता हूं कि ये फाई को एक्सपेरिमेंटली इसकी वैल्यू मेजर करो, क्या करोगे? टाइम जीरो पे बेसिकली ब्लॉक क्या कर रहा है, दैट विल डिटरमिन द वैल्यू ऑफ फाई. फाई इज बेसिकली डिटरमिन्ड बाय व्हाट एग्जैक्टली इज द ब्लॉक डूइंग इनिशियली. लेट मी शो यू दैट. अगर इसमें x t is equal to 0 डालो, t is equal to 0 is the instant at which you start your clock. इसमें क्या आएगा? a cos phi. If you know the amplitude of your motion, you can figure out कि भाई phi क्या होगा. If knowing कि भाई x की क्या वैल्यू है t is equal to 0.
सर जो आपने डिफरेंशियल इक्वेशन सॉल्व की उसमें आपने दो कांस्टेंट्स इंट्रोड्यूस किए, तो सर क्या a का कांस्टेंट जरूरी है इसमें?
हाँ,
ये तो आप जनरल सॉल्यूशन के लिए निकालेंगे, बट लेट्स सपोज अगर हमारा सिस्टम 1 और -1 के दरमियान ऑसिलेट कर रहा है,
हाँ तो फिर तो a की वैल्यू 1 होगी ना. ये देखिए, सपोज करो आपका 0.1 माइक्रोमीटर और -0.1 माइक्रोमीटर प्लस 0.1 माइक्रोमीटर. You don't know, okay? You can redefine your system of units such that amplitude equals 1 unit. Sure, you can do that, okay? But if you're sticking to SI units in general, आपको तो करना पड़ेगा ना, okay? Okay, so you have that. So you can deduce the value of phi based on what the system is doing at t is equal to 0. Another way to see that is कि double derivative ले लो इसका. इसका velocity का function क्या आता है? You have minus omega naught a sine of omega naught t plus phi. And therefore, the speed of the oscillator at t is equal to 0 equals minus omega naught a sine of phi. If you divide this by that, आपके पास क्या आता है? V, the speed of the oscillator divided by the position of the oscillator t is equal to 0 equals a और a कट जाएगा, you will be left with minus omega naught tangent phi. So if you know exactly what the oscillator is doing, how fast the oscillator is moving at the instant when you start your clock, where is the oscillator when you start your clock, you can immediately figure out कि भाई phi क्या होगा. Let me just give you an example. आपका ब्लॉक सपोज करो आपका ये स्प्रिंग ब्लॉक है, एंड यू स्टार्ट योर क्लॉक व्हेन द ब्लॉक इज फर्देस्ट अवे. व्हेन इज फर्देस्ट अवे फ्रॉम इक्विलिब्रियम, उसकी स्पीड क्या होगी? 0. तो फिर ये क्या होगा? लेफ्ट हैंड साइड क्या होगी? 0, क्योंकि डिनोमिनेटर तो नॉन जीरो है ना. व्हेन इज फर्देस्ट अवे फ्रॉम इक्विलिब्रियम, x तो ऑफ कोर्स मैक्सिमम है. So the left hand side is 0 and the right hand side has to imply that phi is 0. तो इस केस में आपका फंक्शन सिंपली क्या आ जाएगा? x naught cosine of omega naught t. I should just write a to be general. And so on and so forth. If you started your clock जब आपका ऑसिलेटर जो है, आपका ब्लॉक जो है यूं हो के फिर यूं के इस तरफ जा रहा है. It passes through the equilibrium position so that at the instant when you start your clock, x is equal to 0. तो फिर आपका you can show from these equations that you get x of t is equal to a times sine of omega naught t, and so on and so forth. Okay, so the value of phi basically determines is related to when you start your clock. You saw something similar when we were doing uniform circular motion. Okay. Right. इसके बाद omega naught के physical significance क्या है? We already know that it has dimensions of inverse time, but physically what is it? It's related to the time period कि कितने time के बाद आपका oscillator वापस उधर ही आ जाता है. So you have x of t is equal to a cosine of omega naught t plus phi. The question is, what is the smallest value of time capital T such that this is true? ये किसके बराबर है? What is the smallest value of capital T such that the oscillator comes back to the same position? फिर आप देखो left hand side में कर लो manipulation. This is equal to a cosine of omega naught t plus capital T plus phi, which I can write as a times cosine of omega naught t plus phi plus omega naught times capital T. Now this has to be equal to a cosine of omega naught t plus phi. That's what I'm saying over here. और फिर ये omega naught times capital T किसके बराबर होगा? Well, that's one solution, but that's boring, okay? उससे अगला क्या होगा? Capital T तो आपने इंतजार ही नहीं किया. If omega naught times capital T is 0, then capital T is 0. इसका मतलब तो आपने इंतजार ही नहीं किया. आपने अभी देखा, दोबारा देख लिया उसी वक्त ही. थोड़ी देर बाद आपने देखना है, कितनी देर बाद दोबारा देखूं सच के आपको ब्लॉक वहीं का वहीं नजर आए. So the cosine function, remember, has a period of 2 pi. So this function will produce exactly the same value as this function when omega naught times capital T is 2 pi or 4 pi or 6 pi or 8 pi or 10 pi and so on. But the smallest value of capital T will correspond to when omega naught T is 2 pi. So you have omega naught times capital T is 2 pi and therefore capital T is, याद आया, red spot. Of course, आपने याद किया होता कि angular frequency is defined as 2 pi over capital T, okay, which is an extremely stupid way of defining it. लगता है जैसे कोई झोली में गिरा था किसी के, okay, उसे यूं हाथ बढ़ाए और उसके झोली में आके गिर गया था. It is now revealed that omega naught must be equal to 2 pi over capital T, okay. Okay, so now we have an understanding what omega naught is. Omega naught is basically the inverse of, up to a constant, it's an inverse of the time period. Okay. Right. So far so good, okay. Acha ji. Okay, so now let's look at something else related to this block spring system. इसकी potential energy क्या होगी at any instant of time? For this block spring system at any, what's the potential energy when the block is stretched by amount x? इसकी potential energy क्या होगी? नहीं, half k x square यार. Right, because you have set up x is equal to 0 at the equilibrium position and you are looking for कि भाई okay, if you stretch the spring by small amount कितनी होगी? Remember, एक upside correct way up parabola आना चाहिए आपको. That's exactly that, okay. So this is u. The kinetic energy is of this block spring system is half mv square. Spring का mass किधर गया? Exactly. You are assuming that the mass of the spring is much smaller than the mass of the block. So you ignore the kinetic energy due to the motion of the spring itself. That's the kinetic energy of your system. What's the total energy? And let's solve for this. V आपको already पता है. The V is precisely equal to that. So this total energy is half m v square, which is omega naught square a square sine square omega naught t plus phi plus half k, and then you have x square, which is a square cosine square omega naught t plus phi. Right? That's the total energy. ठीक है? And now, but however, you also know that omega naught square, remember, is k over m. And therefore, if I plug that in, ये k over m के बराबर है, say bye bye to this m, and you left with half k a square को factor out करो तो बाकी क्या रह जाता है? If you factor out half k a square, देखो इधर भी half k a square है, इधर भी half k a square है, बाकी क्या रह गया? Sine square of this thing plus cosine square of the same thing, which is equal to, and you get that? That's the total energy. The total energy of your harmonic oscillator is independent of time. इधर तो time तो गायब ही हो गया आपका. Of course, because we are not considering any damping. So as the oscillator oscillates, the energy of the oscillator is, the total energy is fixed. And it just depends on the square of the amplitude of your harmonic oscillator. The bigger the amplitude, the more the energy of your harmonic oscillator. Okay? Right? Achha, so much for that. Here's another example. Okay? Those stars हैं आपके, very, of the same mass for simplicity. So there's a star over here, and directly below this star there's another star. ये past exam का problem है, so. Okay, now hopefully अब थोड़े से जाग जाओगे, okay, वो important ऊपर highlight भी करोगे 2 दफा, okay. Red alert, okay. Anyway, ये 2 stars हैं बिल्कुल दरमियान में, of course I cannot draw it exactly in detail, बिल्कुल दरमियान में एक छोटा सा planet है of mass small m. Shh. First question, the question part A, which is just to guarantee you that you're not an illegal drug user, is what's the total force? This is deep space. What is the total force on this planet? 0. Thank you. Okay. So my faith in you has been restored by 5%. Okay. But anyway, okay. तो ये ऊपर एक force है, इधर एक force है, इन दोनों forces का equal magnitude है because this distance is exactly the same as this distance. ठीक है? What's given to you is that the distance between the 2 stars, the centers of the 2 stars to be more precise, is capital L. Okay. अब कोई एस्टेरॉइड आके हिट करता है इस स्टार को, and it hits it in this way. Sorry, इस planet को, sorry, not star को. इस planet को कोई एस्टेरॉइड आके हिट करता है इस planet को, और ये planet थोड़ा सा horizontally of course nudge हो जाता है. Part B, describe the motion of the subsequent motion of this planet. Of course, I mean, ये सारे आपके सीनियर्स इसी तरह के, तो CLO5 must be simple harmonic motion. Okay. ये कोर्स लर्निंग ऑब्जेक्टिव 5 को क्वेश्चन है जो कि सिंपल हार्मोनिक मोशन है, तो इसलिए सिंपल हार्मोनिक मोशन ही हो सकता है. और वैसे भी सर जी ने एग्जाम के आखिर में सवाल दिया है, तो यू नो मैपिंग द लेक्चर नंबर टू द ऑर्डर इन द ऑफ द एग्जाम क्वेश्चन, ये है ही सिंपल हार्मोनिक मोशन सर जी. ओके, ऑब्वियस है, बट क्यों है सिंपल हार्मोनिक मोशन? एक एस्टेरॉइड आके इस प्लैनेट को लगा, ये प्लैनेट की पोजीशन जो बिल्कुल दरमियान में था इनिशियली, वो हॉरिजॉन्टली थोड़ा सा डिस्प्लेस हो गया. क्यों आएगा वापस से? So you have to look at the forces. So imagine that वो बाहर से कहा नहीं, अच्छा वो देखो उसे कह रहा हमारे ऊपर ऐसी सर्दी आप कह रहे हैं, बाहर से आवाजें आ रही हैं. Imagine this is distance x. Distance x is the horizontal displacement of the planet from its initial equilibrium position. Just like x over there was the horizontal displacement of the block from its initial equilibrium position. X of course change over every time. This is just a snapshot of the situation. किसी भी particular time पे ये है value of x. As time goes on, of course, x continuously changes. And we figure out कि x किस तरह change हो रहा है. The claim of course is that x of t is the amplitude of the motion times cosine of omega naught t plus phi. That's the claim कि simple harmonic motion है. Okay? But we have to show कि क्यों है simple harmonic motion. अगर कोई मैं शो करूं कि ये मोशन सिंपल हार्मोनिक मोशन है, क्या आपने शो करना एग्जैक्टली? That basically the variable that describes the motion जो कि x है, the double derivative of that with respect to time is equal to negative minus sign times some constant times the same function. If over here x satisfies an equation that looks like this, you must have simple harmonic motion, क्योंकि उसका solution जो है that is your typical periodic cyclic behavior characteristic of simple harmonic motion. तो आपने ये show करना है कि Newton's second law leads to an equation that looks like this. Okay, so for that of course you have to figure out the forces acting on this. तो थोड़ा सा मुझे अब exaggerate करने दो, ये थोड़ा सा for, तो ये आपका planet इधर है, काफी मैंने exaggerate किया, असल में x बहुत छोटा सा होगा. तो इधर आपकी एक लाइन है, इधर आपकी एक लाइन है, there's a force that is acting like that, there's a force acting like that. These two forces are equal in magnitude because this distance is the same as this distance. What is this distance? Or just to keep the mathematics simple, हम ऐसा करते हैं कि बजाय L/2 stupid से L/2 से deal करने के, we'll define this half distance as L, ताकि ये भी distance L हो जाए. So I don't have to deal with stupid fractions, okay? Okay, so anyway, so the distance between the two stars is now 2L. अच्छा, अब ये force, ये वाला distance किसके बराबर होगा? ये वाला distance. You have this right angle triangle. हजरत पाइथागोरस ने आपको बताया था, और for those जो कि फारसी या उर्दू से ज़्यादा मुंसलिक हैं, हजरत फीसागोरस ने कहा था कि पाइथागोरस थ्योरम को बाय द वे मसला है फीसागोरस कहते हैं, ओके, बता नहीं हुए, ओके. सो यू हैव दैट. सो ये डिस्टेंस किसके बराबर है? L square plus x square, square root of course. अच्छा बाहर है, ओके. ये वाला डिस्टेंस किसके बराबर है? Of course exactly the same. So what's the total force acting on the planet when it is a distance x away, horizontal distance x away? Well, एक force तो ये लग रही है और एक force ये लग रही है, लेकिन ये that's not the total force of course. I have to take the vector sum of these two forces. इन दो forces के vertical components तो cancel हो जाएंगे. Only the horizontal components will of course add. तो अगर ये मैं एंगल कहूँ कि ये एंगल थीटा है, तो बाई सिमेट्री ये एंगल भी थीटा ही होगा. So the total force acting on the planet is F cos theta plus F cos theta, which is 2F cos theta. Of course, technically speaking, अगर ये मैं axis का positive ले रहा हूँ, this will be minus 2F cos theta because the force is acting to the left. But never mind. Right now, let's just concern ourselves with the magnitude. So yeah, this is the magnitude of the total force acting on the planet when the planet is x horizontal distance away from its initial equilibrium position. Okay? And this is equal then by Newton's law of gravitation, Gmm divided by the distance squared between this planet and this star. What's the distance squared? L square plus x square times cosine of theta. लेकिन cosine of theta in terms of these variables किसके बराबर है? ये base किसके बराबर है? Hypotenuse किसके बराबर है? तो cosine theta is nothing other than x divided by square root of L square plus x square. That is the total force acting to the left on your planet. And then of course you can tidy this up. You can have 2gmm divided by L square plus x square raised to power 3 by 2 times x. That is the total force acting to the left. So अगर मैं इसको vector के form में लिखूं, I'll be writing this as minus. This almost looks like the same as your block spring thing. You have minus kx times ex, except that there's one issue. यहाँ पर k constant नहीं है इस केस में. k is a function of x. k के अंदर ये जो आपका k जो है, so called ये जो k फेयर है, ये brackets के अंदर, इसके अंदर भी तो x है. But you didn't make one assumption yet. Simple harmonic motion में एक जो बड़ा common assumption मारते हो. चला गया कहीं? Oh, never mind. If you have a system in equilibrium, you disturb it slightly. As in x is much smaller than L. If x is much smaller than L, much smaller than L, you remember your astronomical distances are इधर. x will be much smaller than L. तो L square plus x square to the very first approximation किसके बराबर है approximately? L square के बराबर. Of course numerator में ये जो x है इसको नहीं मैं कुछ कहता क्योंकि ये किसी के साथ ऐड नहीं हो रहा. So this x remains as it is. But to a very good approximation, L square plus x square is just equal to L square. If you're not convinced, एक चीज आपने की थी मैथमेटिक्स में A levels में the binomial expansion. याद आया? Of course नहीं याद आया, okay. But L square plus x square आप कर रहे हो raised to power -3/2. As in क्योंकि -3/2 इसलिए लिखा है क्योंकि डिनोमिनेटर में है ये. I'm going to look at what is this thing approximately equal to when x is much smaller than L. So to do that, first of all I do L square को factor out कर लेता हूँ. मेरे पास 1 plus x square over L square मैं लिख देता हूँ और फिर ये आ जाता -3/2. And this is then equal to L raised to power -3. ये -3/2 पावर इधर भी आ जाएगी, इधर भी आ जाएगी. And you have L raised to power -3 and then you have 1 plus x square over L square raised to power -3/2. और ये किसके बराबर है approximately? याद आया 1 plus x raised to power whole raised to power n when x is small is approximately equal to 1 plus nx. क्या हो गया? Okay, so this is approximately equal to 1 minus 3/2 x square over L square. और फिर आपका 1 over L cube है. So you can immediately see कि अगर x बहुत छोटा है L से तो x square over L square तो बहुत ही ज्यादा छोटा है. तो that's why to a very good approximation approximately L cube के बराबर है. आपका error सिर्फ x over L में नहीं है. आपका error जो है वो x square over L square में आएगा. If x is much smaller than L, then x over L is small, but x over L whole square is even smaller. So to a very good approximation, you can just drop this plus x square. इसे मैं किया था ताकि आप convince हो जाए कि वाकई this is a very good approximation in this case, and you're left with just L cube over here. और फिर अब आपका क्या है? This is basically minus kx. कोई spring नहीं है. And yet again, the total force acting on a system which is disturbed slightly from equilibrium is basically exactly of the same mathematical form as the force acting on a block spring system. देखो मैंने आपको galactic scales में भी दिखा दिया है, okay? Okay, so you have essentially that the total force is देखो या एक मैंने आपको माइक्रोस्कोपिक स्केल पे एग्जांपल दी है, एक आपको ऑर्डिनरी स्केल्स पे एग्जांपल दी है, एक आपको एस्ट्रोनॉमिकल स्केल्स पे भी एग्जांपल दे दी है, ओके, ऑफ द सेम थिंग, ओके, दैट यू हैव अ सिस्टम इन इक्विलिब्रियम, यू नudge it slightly, you get simple harmonic motion. So you have that the total force is minus आप कह देते हो -2gmm over L cube x ex. अब मैं कहता हूं इस ये अब ठीक है आपने प्रूव कर लिया सिंपल हार्मोनिक मोशन है बिकॉज द फोर्स एक्टिंग ऑन योर प्लैनेट इज प्रोपोर्शनल टू x पॉइंटिंग इन द ऑपोजिट डायरेक्शन माइनस साइन रिस्टोरिंग फोर्स है. फाइंड आउट द टाइम पीरियड ऑफ दिस मोशन. कैसे निकालोगे? You basically have that this must be equal to by Newton's second law, this must be equal to mass times the acceleration. और फिर ये mass और ये m और m काट जाएगा, where so the mass of the planet doesn't matter. d2x by dt2 क्या आ रहा है आपके पास? minus 2gm over L cube times x. That's what you're getting. और फिर आप कह दो तो इसको मैं डिफाइन कर देता हूं as minus omega naught square, where omega naught square is now equal to 2gm over L cube. So the natural angular frequency of this motion is simply the square of the natural angular frequency is just equal to 2gm over L cube. अगर मुझे omega naught पता है, of course I know capital T. Capital T is just 2 pi over omega naught. So from here I identify कि इस मोशन के लिए omega naught square जो है वो k over m के बराबर नहीं है. इस मोशन के लिए omega naught square जो है वो 2gm over L cube के बराबर है. and therefore from here t is equal to 2 pi over omega naught. The rest is just algebra. Okay, ठीक है. Okay, so much for that. Because the force is pointing to the left. I'm taking my position. जिस तरह वही block spring system की तरह. Okay. Now, this situation of course is not as simple as I made it sound to be. अगर सपोज करो आपका एस्टेरॉयड जाके इधर हिट करता, सच कि ये प्लैनेट ऊपर की तरफ नज होता, फिर क्या होता? तो फिर तो रिस्टोरिंग फोर्स नहीं लगनी थी, फिर तो आपके प्लैनेट ने ओ ऊपर जाते जाना था उस स्टार की तरफ, फिर ऑसिलेटरी मोशन नहीं होना था, इवन तो आपका इक्विलिब्रियम पॉइंट से ही नाच हुआ है, वो आपका प्लैनेट आप थोड़ा सा ऊपर नाच हुआ है, फिर ऊपर ही जाता जाएगा, राइट? सो अब आपको कैलकुलस 2 की कॉम्प्लेक्सिटीज नजर आ रही हैं. दिस इज एसेंशियली आपका, आप जो प्लैनेट जो है वो 3D स्पेस में मूव कर सकता है. व्हेन इट मूव्स इन वन डायरेक्शन आपका पोटेंशियल एनर्जी का मिनिमम आ रहा है, व्हेन इट मूव्स इन द अदर डायरेक्शन आपका पोटेंशियल एनर्जी का मैक्सिमम आ रहा है. एक डायरेक्शन में आपका अनस्टेबल इक्विलिब्रियम है, दूसरे डायरेक्शन में स्टेबल इक्विलिब्रियम है. So if you have a function of two variables, as you'll see in your calculus 2 course, इतना आसान नहीं होता बताना कि ये मैक्सिमम पॉइंट है, मिनिमम पॉइंट है. हो सकता है किसी डायरेक्शन के लॉन्ग मिनिमम हो, किसी डायरेक्शन के लॉन्ग मैक्सिमम हो. Okay? अगर आपने कभी हॉर्स राइडिंग की है, यू माइट हैव सीन द शेप ऑफ अ सैडल. वो सैडल जो है यूं होती है, और फिर अगर आगे से देखो तो यूं होती है, अगर साइडों पे देखो तो यूं होती है. तो अगर आगे से देख रहे हो, आप यूं करके देख रहे हो तो आपको मिनिमम पॉइंट नजर आ रहा है एट द मिडल ऑफ द सैडल. अगर यूं देख रहे हो तो आपको मैक्सिमम पॉइंट नजर आ रहा है एट द सैडल. सो सच अ पॉइंट इज नोन एज अ सैडल पॉइंट. ओके, सो एनीवे आई लीव दैट एज अ प्रीव्यू ऑफ कैलकुलस 2, जो कि ऑफ कोर्स क्योंकि आप सीएस कर रहे हो ज्यादातर लोग नहीं करेंगे, सो नेवर माइंड. ओके, सो लेट्स डू द सिंपल पेंडुलम. भाई ये सिंपल पेंडुलम को सिंपल क्यों कहते हैं भाई? That's an interesting question. Okay? ये सिंपल पेंडुलम आप सारे 5 साल आप सिंपल पेंडुलम सुनते आए थे और पढ़ते आए थे, उसको सिंपल क्यों कहते हैं? There are things called compound pendulums, there are things called physical pendulums. What you do in high school or below is a so-called simple pendulum. इधर सिंपल क्या बता रहा है आपको? नहीं, it's not related to that. That just emphasizes that the size of your pendulum bob is negligible. You massless नहीं, वो massless तो physical के लिए भी वही assume करते हो. आप basically assume कर रहे हो कि इसका size ना होने के बराबर है. The size of this pendulum bob compared to the length of the string is much smaller. Okay? If you had a big sphere और उस पे अगर oscillation करो, you'll find out कि सर ये square root और ये 2 pi square root L over G तो violate हो रहा है. Time period. Okay, of course it's violated because that theory, you have to modify your theory to deal with the case where the size of the pendulum bob is significant. तो इस केस में क्या करते हो? आपका ये स्ट्रिंग है, यूं एंगल थीटा है, तो फिर क्या करो? How do I show that this is simple harmonic motion? इस केस में it's much simpler to do it in terms of rotations. The bob is simply just rotating about this fixed point. आपका जो bob जो है वो सिर्फ इस point के गिर्द rotate कर रहा है यूं करके. It's just swinging in a circular arc whose center is this point. It's swinging in a circular arc of radius equal to the length of the string, क्योंकि उसका अपना size negligible है. So let's look at what's the torque acting on the pendulum bob when it is over here, when it makes an angle theta with the vertical. What's the torque acting on your pendulum bob? सोच के बताना, otherwise my faith in you goes back to 0%. Okay, ये थीटा ये है, तो ये एंगल थीटा है, mg cos theta is passing through the point about which you are calculating the torque. तो mg cos theta जो कॉम्पोनेंट है उसकी वजह से टॉर्क जीरो होगा. mg sin theta ये है आपका, mg sin theta की वजह से टॉर्क क्या होगा? mg sin theta times L. L is the perpendicular distance between this component and the point about which you are calculating the torque. So the torque is simply mg sin theta times L, where L is the length of the string. And this bob is just executing pure rotation about this point. तो torque किसके बराबर होगा? For pure rotation, how do you relate the angular acceleration to the torque? और क्या हो गया? फ्राइडे को क्विज भी है, खोल लो किताबें. How do you relate torque to the angular acceleration for pure rotation? Thank you. इतना mental inertia क्यों है इतना? This is equal to I alpha. Of course इसमें कोई गड़बड़ है. क्या गड़बड़ है? Alpha of course I write as ये टॉर्क आपका रिस्टोरिंग टॉर्क है. द टॉर्क इज ट्राइंग टू डिक्रीज द वैल्यू ऑफ थीटा. तो इधर ऑफ कोर्स यू हैव टू डू इट मोर रिगोरसली, लेकिन दैट इट्स इनफ टू जस्ट टू रियलाइज दैट फिजिकली द टॉर्क विल रिड्यूस द साइन ऑफ थीटा एज टाइम गोज ऑन. इसलिए इधर माइनस होगा. अगेन यू कैन रिड्यूस द डायरेक्शन ऑफ द टॉर्क मोर रिगोरसली इफ यू वांट, बट दिस इज गुड इनफ. इस केस में मोमेंट ऑफ इनर्शिया किसके बराबर है? मैं दोबारा जान नमाज निकाल के नफल पढ़ने बैठ जाता हूँ. या टेल मी कि किसके बराबर होगा? थ्योरम शुरू ना बताओ, टेल मी कि एग्जैक्ट फॉर्म क्या होगा? आईसीएम क्या है इस केस में? नहीं, बुक की जरूरत ही नहीं है. इट्स ऑब्वियस कि क्या है. एक पॉइंट पार्टिकल, आपका बॉब पॉइंट पार्टिकल है यार. मोमेंट ऑफ इनर्शिया होता क्या है? मास ऑफ ए पार्टिकल टाइम्स द डिस्टेंस स्क्वायर्ड फ्रॉम द एक्सिस ऑफ रोटेशन. इधर एक ही पार्टिकल है आपका, स्ट्रिंग तो मासलेस है, इसका डिस्टेंस क्या है फ्रॉम दिस पॉइंट? L. तो मोमेंट ऑफ इनर्शिया क्या होगा? मास ऑफ द बॉब टाइम्स L स्क्वायर्ड. दैट्स इट. सम करने की तो जरूरत ही नहीं इस केस में. सम में है ही एक टाइम, एक ही पॉइंट पार्टिकल है सिर्फ आपका. सो दिस इज. और यहाँ अगर आपने पैरेलल एक्सिस थ्योरम लगाना ही था तो आप कहते हैं ICM प्लस m टाइम्स द डिस्टेंस स्क्वायर्ड. लेकिन ICM इस केस में क्या होगा? जीरो, बिकॉज दिस इज अ पॉइंट पार्टिकल. ये कहा था, चलो भी ठीक है. ओके, सो दिस इज इक्वल टू ml स्क्वायर टाइम्स दी. और फिर आपका m और m देखो कट गया, राइट. एंड देन यू हैव कि ये l और ये हो गया. और फिर आपके पास आ गया कि द डबल डेरिवेटिव ऑफ थीटा विल बी इक्वल टू the double derivative of theta with respect to time will be equal to minus g over L sin theta. If now I make the approximation that theta is small, sin theta from the Taylor series of sin of theta is approximately equal to theta for theta small. So that is why the pendulum only displays simple harmonic motion for small amplitudes. अगर थोड़ा सा नाच करो तब भी सिर्फ वो हार्मोनिक मोशन रहता है. थोड़ा सा ज्यादा कर दो तो वो आपका टाइम पीरियड चेंज हो जाता है. So you have this thing will be equal then to minus g over L times theta. पहचानी? मैंने approximate किया कि sin theta is approximately theta if you assume that theta is small. ये किया था बूट कैंप में, और उसके बाद भी किया था. टेलर सीरीज है. द टेलर सीरीज ऑफ साइन ऑफ थीटा इक्वल्स टू थीटा माइनस थीटा क्यूब ओवर 3 फैक्टोरियल प्लस थीटा रेज़ टू पावर 5 ओवर 5 फैक्टोरियल माइनस 10. अगर थीटा छोटा है, यू कैन थ्रो दिस अवे, यू कैन थ्रो दिस अवे एंड सो ऑन एंड सो फोर्थ. यू आर लेफ्ट विद दैट. ओके, और इधर से फिर बताओ ओमेगा नॉट स्क्वायर किसके बराबर है? फॉर दिस मोशन व्हाट इज ओमेगा नॉट स्क्वायर? नहीं, नेगेटिव तो वैसे ही आता है ना, वो तो. सो ओमेगा नॉट स्क्वायर इज जस्ट इक्वल टू g ओवर L, एंड देयरफॉर ओमेगा नॉट इज इक्वल टू स्क्वायर रूट ऑफ g ओवर L, एंड देयरफॉर टाइम पीरियड इज 2 पाई ओवर ओमेगा नॉट, व्हिच इज 2 पाई स्क्वायर रूट L ओवर g. पहचाना? Okay.